focusing on Newton's laws. Fortunately, Sir Isaac Newton has been dead for a couple centuries now, so he won't be here to introduce his own laws, but we will be presenting it through a stand-in, which is Kimmie Baxter, who is me. So, first law is the law of inertia. We can define inertia as the resistance to change in motion. So this gives us a pretty good indication about what our first law might be talking about, which essentially states that an object in motion will stay in motion while an object in rest will stay at rest unless a force acts upon it. Or, if you want to be a little more scientific with it, you could say that if net force equals 0, something in motion will move at a constant velocity, whereas a still object will stay still. So for example, if I take this apple is going to stay still right here as long as I hold it, because nothing is going to make it move. It's at rest, so it'll stay at rest. Now, if a force is applied to it, it no longer stays at rest. It moved. This goes in line with Newton's first law. So what does this first law give us? It gives us momentum. Momentum is the quantity of motion based off of mass and velocity. So we can write this as momentum, big M, equals mass, little m, times velocity. This is going to be measured in kilograms times meters over seconds. So this gives us our law of conservation of momentum, which essentially states that the momentum from the start will be the momentum at the end if you have an impact. So M1 equals M2, which you can write in these two different ways. You can say that your first momentum will equal your last momentum in the sense that mass 1 times velocity 1 equals mass 2 times velocity 2, or you could say that mass 1 times velocity 1 plus mass 2 times velocity 2 equals mass 1 plus mass 2 times velocity. Now that sounds a little bit crazy, and you're probably wondering why there's a lot of different numbers, which is totally fine, but we use these two different ones for the different types of impacts we have. So if you have an elastic impact, you're going to use this first one. So an elastic impact occurs whenever two objects hit each other, but then they kind of bounce off of each other. So essentially, the velocities remain pretty consistent. The second one can be used in what we call a plastic impact. In plastic impacts, what happens is two objects collide, but then they kind of go together because one of them deforms. So they become one object, hence why you have the mass of 1 and the mass of 2 times the new velocity as they move together. So the way that we figure out the different types of impacts, if it's more elastic or plastic, is based off of a coefficient of restitution, but we're not going to go into how you calculate that or get that right now. But that basically is how we figure out if it's elastic or plastic. Most impacts in general are going to be a combination of both elastic and plastic. So that's Newton's first law. Newton's second law is going to be the law of acceleration. So if we define acceleration, acceleration is the change in velocity over time, or we can write it as A equals delta V over T. So the second law states that F equals ma, or that the net force equals the object mass times the object acceleration. So if an external force is applied, the object will accelerate. Essentially, if you apply a force, you're going to have acceleration. Now there are a lot of different ways that you can write this out orderly and have a lot of different explanations, but this is the most basic way, bare bones way to write this law. So if we wanted to figure out the acceleration of this apple, if I chucked it across the room, which I'm not going to do because that'd be really mean to do to people to clean up. Essentially what you would say is how much force was applied to that apple, and then what is the object's mass, and you would write it a little bit differently. So if we're trying to find the object acceleration, you would say F equals ma, and you would just reorient it so it says F over m equals a, and you could get the acceleration of the apple. Now it's really important to note that if you're going to do this, you have to take the object's mass. So you wouldn't take the mass of me throwing it, you would take the mass of the apple to figure out the acceleration of the apple. So what does this law give us? This law gives us impulse. Impulse is equal to the product of force in time over which force acts. So this describes the motion from a magnitude and a duration of force standpoint. So I equals F times T, and we measure this in Newton seconds. And we can actually relate this back to momentum. So we can see that you have a impulse-momentum relationship, and this is how it's defined. You can see that the impulse, which we have our net force times time, equals mass times delta V, which is momentum. So the reason why this is so applicable to this law is because it's actually just going to be a way to rewrite the second law, and I can explain how. So if we look at the second law, again, we see it's F equals ma. So if we expand this, we still have F equals mass, and then we already defined acceleration up here as delta V over delta t. So delta V, delta t, and then we can just do some rearranging. So this would give us F times delta t equals m times delta v. And as we should all know, delta v is just going to essentially be the final velocity minus the initial velocity. And that gives us that equation. So, just to recap that really fast, this is just a rewriting of Newton's second law and explains the different correlation between momentum and impulse, which is super beneficial in everyday life because, for example, it's how airbags work. We know that because we have more time based off of an airbag, our force will be diminished, which is great. So, for our third law, we've got the law of reaction. The law of reaction is based off of a response to an action, which is what we can define reaction as. And the third law states that to every action, there's an opposite and equal reaction, or we can call them action-reaction pairs. So essentially, that's saying that the force I'm applying to this wall right now, or this whiteboard, is the same force that it's applying back to me. So whatever force I apply, it's applying back to me. So you could say that F of Kimmie on the board is equal to the force of the board on Kimmie. And that's how we can write these. It's pretty simple, straightforward, but just that every action has an equal and opposite reaction. So what does this one give us? It gives us a really awesome law. There's really nothing else. And it actually gives us the end of Newton's laws, which is great, because now we can just do a quick recap. So to go over what we already kind of talked about, we have the different laws. We have law 1, which is the law of inertia, which essentially states that if an object is in motion, it'll stay in motion. If an object is still, it'll stay still. So remember that apple and how that apple stays still if I don't move it. We also have the law of acceleration, which tells us the net force is going to be equal to the object's mass times the object acceleration. So remember me chucking that apple and figuring out what its acceleration is based off of that law. Then we also have the law of reaction, which we just went over, that states that there's an equal and opposite reaction to every action that occurs. So just remember pushing against that board. So what each of these give us? You have law 1, which gives us momentum, which we went over as m equals mass times velocity. And you have conservation of momentum, that essentially the momentum from the beginning is going to be the same as the momentum at the end. We also have law 2, which gives us impulse, which is the force, the magnitude of the force times the duration that it lasts, so the time, so I equals F times t. And it gives us the impulse-momentum relationship, which I will not go through that long strand of symbols again, but just remembering that that's a rewrite of Newton's second law. So that's all that we have. And of course, I am not Isaac Newton as stated before, unfortunately, so I do have some lovely references that I got all of this information from. And overall, thanks for watching.